fundamental, maybe even a bit mind-bending, the electron. And there's this paradox, right? How can every single electron be perfectly identical to every other one, but still be, well, unique? How does it have its own place? We think exploring this is actually a neat shortcut to understanding some really deep physics.
That's a great way to put it.
Yeah.
Yeah, this really pushes us past our everyday ideas about, what it means for something to be this thing in this spot. And the answer, it lies right in quantum mechanics. Things like quantum indistinguishability and the whole idea of a quantum state. What's so cool is that the electron being absolutely identical isn't the problem for uniqueness, it's actually the reason for it.
Okay, I'm ready. Let's follow that shortcut. I really want to get how these quantum rules flip sameness into singularity. Right, let's start there. This idea of perfect uniformity. When we say all electrons are identical, what are we actually saying? Is it like, two super well-made ball bearings?
It's much, much more fundamental than ball bearings. It's not just close. It's perfect sameness, indivisible. Every single electron, no matter where or when, has its exact same set of built-in properties. Intrinsic properties. These aren't just averages, they are truly fundamental constants. Like there's one single perfect blueprint for electron used everywhere. Take its mass, for example. Every electron has exactly the same invariant mass. Tiny, yes, but precisely defined. A fundamental constant. We've even got astronomical data suggesting the ratio between a proton's mass and an electron's mass hasn't changed in like 7 billion years or more?
Yeah.
Half the age of the universe.
Wow, okay. That stable across cosmic time, that really drives home how fundamental this identity is.
It really does.
Yeah.
And then there's the charge, the elementary charge. Again, precise, indivisible. The basic unit of electric charge.
Yeah.
-1 elementary charge for every electron. And its spin. Every electron is what we call a spin 12 particle.
Spin 12. That sounds technical.
It just means it has this fixed amount of intrinsic angular momentum, like a tiny fixed amount of spin, always res O2. Now, we can measure its orientation, like up or down, relative to something, but the total amount of spin, that S12, is the same for every electron, always.
So it's not literally spinning like a little ball, but it inherently has the spin property.
Exactly. It's just part of what makes an electron an electron. And on top of that, they're elementary, no smaller parts we know of, and they're incredibly stable. Their lifetime is estimated to be ridiculously long, like 10 to the power of 28 years. Way older than the universe.
Right.
Which is good, because if they decayed, it would mess up fundamental laws like charge conservation.
Okay, got it. Perfectly identical particles. But here's the mental block, right? If they're so identical, how does the universe treat them as distinct things? In our world, even identical twins have different spots, different paths. How does quantum mechanics just throw that out?
Right, that's the quantum shift, the first big turn on our shortcut. Classically, yeah, you could imagine labeling electron A and electron B and tracking them. They'd have their own little histories.
Yeah.
But quantum mechanics says, nope, no definite paths. Instead, you have this wave function, a cloud of probability. And there's Heisenberg's uncertainty principle. You fundamentally cannot know both exactly where an electron is and exactly where it's going simultaneously. So the idea of a nice continuous path, it just dissolves. It's not that we're bad at measuring. Reality itself is fuzzy at that level. And here's the kicker. When the wave functions of two identical particles, say two electrons, overlap in space, there's literally no way, not even in principle, to tell which is which.
No way at all.
None. If you detect an electron in that overlap zone, asking, was that electron A or electron B, is meaningless. It's what we call ontological indistinguishability. The whichness just isn't there. It's not a lack of information. It's a lack of identity in the classical sense.
Okay, hold on. If they're that indistinguishable, fundamentally lacking witchfruitness, how on earth do they end up being unique individuals occupying distinct states? This seems like the core of the paradox. How does sameness force uniqueness?
This is where quantum mechanics gets really elegant, I think. It comes down to something called the indistinguishability postulate. Basically, it says the overall wave function for a bunch of identical particles has to behave in a very specific way if you swap any two of them. And this rule splits all particles into two families. You've got bosons. These have integer spin, like photons. If you swap two identical bosons, their combined wave function stays exactly the same, symmetric. And because of that, any number of bosons can pile into the exact same quantum state. Think lasers or Bose-Einstein condensates. They're like sociable particles.
Okay, bosons are fine sharing a state. What's the other type?
The other type is fermions. These have half-integer spin. And electrons, protons, neutrons, they're all fermions. For fermions, if you swap two identical ones, the entire wave function flips its sign. It becomes negative. It's antisymmetric. Electrons are spin 12, so they're fermions. And this anti-symmetry, that's the absolute key.
Anti-symmetry. So the math description flips its sign. how does that prevent them from being in the same state? What does that minus sign actually do?
Great question.
Okay.
It leads straight to probably the most famous rule that comes out of this, the Pauli exclusion principle. It's not some extra rule tacked on. It falls right out of that anti-symmetry requirement. The principle says, no two identical fermions can be in the exact same quantum state at the same time within the same system, like an atom.
Okay. So for electrons in an atom, they can't have the same quantum numbers? Is that it?
Exactly the same set of 4 quantum numbers. You can see why mathematically. If you try to write down the antisymmetric wave function for 2 fermions in the identical state, let's say state A, the formula forces you to write something like wave function of 1 in state A times 2 in state A minus wave function of 2 in state A times 1 in state A.
Yeah.
Well, those 2 terms are identical. So you subtract something from itself and you get 0.
Zero, meaning?
Meaning the probability of finding them in that state is 0. It simply cannot exist. The universe forbids it. So you see, it's because they're identical fermions demanding this antisymmetry that they're forced into having unique quantum states. Sameness enforces uniqueness. The exclusion principle is the identity principle applied to fermions.
That is, wow, okay, so the universe makes each electron carve out its own little niche, its own identity marker. What does that niche or state actually look like? It's not just a point in space, right?
No, definitely not a point. The Pauli principle guarantees this unique quantum state, and that state serves as its unique address in spacetime, you could say. But the address isn't coordinates like on a map. It's defined by this set of 4 quantum numbers, and these numbers describe the electron's wave function. For an electron in an atom, getting a unique set of these 4 numbers means it has its own distinct state. Pauli says no other electron in that atom gets the exact same set. It's like the universe issues a unique ID based on these numbers, making each electron distinct within that system, even though the electrons themselves are fundamentally identical. That's the solution.
Okay, let's break down those 4 numbers. What are they telling us?
Sure. First, there's the principal quantum number called n. It's a positive integer, 1, 2, 3, and so on. It basically tells you the main energy level and sort of the average distance from the nucleus. Think of it like the main shell the electron is in.
Right, like the shells in those simple Bohr models, but more complex.
Exactly. Then you have the angular momentum quantum number, L. This can be 0 up to n minus 1. This number determines the shape of the electron's probability cloud, the subshell. L1 is an s orbital spherical. L1 is a p orbital sort of dumbbell shaped. L2 is d, more complex shapes, and so on.
Okay, shape. What's next?
The magnetic quantum number, L sub L. This tells you the orientation of that orbital shape in space. It can range from LL up to plus L. So for p orbital L1, you can have ML1 is 1, 0, plus 1, corresponding to orientations along the x, y, and z axis, roughly speaking.
Energy level, shape, orientation. What's the 4th?
The last one is crucial. The spin projection quantum number, sums S. And for an electron, this can only be plus 12 or negative 12. We often call this spin up and spin down. This is the quantum number that allows 2 electrons to share the same spatial orbital, same N, L, and ML, provided they have opposite spins. Their spin states make their overall quantum states unique.
So that's how you can fit 2 electrons in one orbital box in chemistry diagrams. Opposite spins give them unique full addresses.
Precisely. A unique set of N, L, ML, and Ms defines a unique quantum state, a unique wave function. And the square of that wave function gives you the probability of finding the electron somewhere in space. That probability cloud is the orbital. So an electron's unique place is its unique probability distribution in spacetime, enforced by Pauli.
Okay, this makes sense theoretically, but how does this abstract rule actually, build the world we see? Does it have tangible consequences?
Oh, absolutely. Enormous consequences. This isn't just theory. It's basically the architect of, well, almost every material. The whole structure of atoms, the way they interact, chemistry, the properties of materials, it all flows from this exclusion principle. It forces electrons to arrange themselves in a structured way, filling up energy levels or shells.
You mean like they can't all just fall into the lowest energy level near the nucleus?
Exactly. That lowest level, the 1's orbital, can only hold 2 electrons, one spin up, one spin down. Think about building atoms. Hydrogen has 1 electron, it goes into 1s. Helium has 2, they both fit in 1s with opposite spins. But now lithium comes along with 3 electrons. That 3rd electron, it's excluded from the 1's orbital, it's full. So it's forced to go into the next available energy level, the 2's orbital.
I see. So it's like filling seats in a theater, section by section, because no 2 people can sit in the exact same seat.
That's a great analogy. And this step-by-step filling process, following the Pauli principle and energy levels, that's what gives us the periodic table. Elements in the same column. They have similar arrangements of electrons in their outermost shells, and that's why they behave chemically alike. Why are noble gases like neon or argon so stable and unreactive? Their outer shells are completely full, very stable configuration. Why are alkali metals like sodium so reactive? They have one lonely electron in their outer shell, eager to participate in bonding. The entire logic of chemistry, how atoms bond to form molecules, the shapes of molecules, the hardness of a diamond, the conductivity of copper, it all fundamentally traces back to electrons being fermions and obeying the exclusion principle. It's why matter takes up space and doesn't just collapse.
That's incredible. So this one quantum rule dictates the structure of everything. Okay, let's shift gears a bit. What does this do to our philosophical ideas about identity? It feels like it fundamentally challenges how we think about what it means to be an individual thing.
It really does, deeply. It runs right up against a very old philosophical idea called Leibniz's principle of the identity of indiscernibles, PII for short. The basic idea of PII is if you have two things and they share all the same properties, then they can't actually be two things. They must be one and the same thing.
But quantum mechanics seems to say electrons can share all intrinsic properties and even some relational ones in certain situations, yet we still count them as two.
Exactly. In quantum mechanics, you can have, say, two electrons in an entangled state where they possess all the same intrinsic properties, mass, charge, spin, and even symmetric relational properties. Yet the formalism treats them as numerically distinct as two electrons. This has led to a big debate in the philosophy of physics. What exactly are these quantum entities? It creates what they call metaphysical underdetermination. The physics allows for different interpretations.
So what are the main interpretations? Are they individuals or something else?
Well, one view, maybe the dominant one among philosophers of physics, is the received view. It suggests that quantum particles like electrons aren't really individuals in the classical sense. They're more like excitations or knots in a quantum field. Temporary patterns. Our everyday language of this particle and that particle is just a convenient shorthand that doesn't quite capture the reality. People have even tried to develop new kinds of logic, like quasi-set theory, to handle collections of objects that might lack classical identity.
Wow, new logic systems. What's the alternative view?
The alternative is basically to say, no, electrons are individuals. They have some kind of primitive thisness. Philosophers sometimes call it haecidi, a brute fact that this electron is this electron, even if we can't point to a property that makes it so. On this view, it's Leibniz's principle, PII, that fails at the quantum level, not the individuality of the electron. This whole philosophical tangle is actually really useful because it highlights where our understanding of the physics itself might be a bit awkward or incomplete. Like physicists talk about tracking individual particles in experiments, but the underlying theory seems to describe something more like waves or field excitations that aren't really localized individuals until measured. There's a tension there.
Okay, that's a deep rabbit hole. To wrap things up, thinking about this whole identity puzzle, was there any really out there radical idea that came from someone wrestling with this?
Oh, definitely. One of the most mind-bending came from the physicist John Wheeler. He apparently called Richard Feynman one day and proposed his one-electron universe idea.
The one-electron universe, what does that even mean?
Wheeler's idea was, well, what if there's actually only one electron in the entire universe? And what we perceive as all the countless electrons everywhere is just this single electron weaving back and forth through time. Its world line would be incredibly tangled. It would travel forward in time, then backward, appearing as a positron, its antiparticle, then forward again. If you took a snapshot of space-time at one moment, you'd see this single world line intersecting our present many, many times. And each intersection looks like a different electron or positron.
Wait, so all electrons are identical because they literally are the same single entity, just seen at different points in its time-traveling journey?
That was the radical proposal. It solves the identity problem in the most extreme way possible by eliminating the multiplicity altogether. Now, empirically, it doesn't quite work. The big problem is the matter-antimatter asymmetry. We see way more electrons matter than positrons antimatter. If it was one entity zigzagging, you'd expect roughly equal amounts.
Okay, so it didn't pan out as a full theory.
No, but its influence was huge. Feynman was really taken by the core insight that an antiparticle, like a positron, could be mathematically treated as a particle moving backward in time. He basically ran with that piece of the idea, and it became absolutely central to his development of quantum electrodynamics, QED, which is one of our most successful physical theories ever. So even though the one-electron hypothesis itself wasn't right, wrestling with that extreme consequence of identity led to a huge leap forward in physics. It really highlights the power of tackling these fundamental identity questions. So just to bring it all back together, The electron's identity, its perfect sameness, comes from its intrinsic properties, mass, charge, spin. That's the universal template. But its uniqueness, its individuality within a system, is extrinsic, it's relational. It comes from its quantum state, defined by those 4 quantum numbers, a state it's forced into because it's an identical fermion, thanks to the Pauli exclusion principle.
It really is elegant when you put it like that. The rules that make them fundamentally the same are the very rules that guarantee no two can be the same in terms of their state. Sameness mandates singularity. So think about this next time you look at the world, all the complexity, the diversity, the structure, from chemicals to stars to life itself. It all hinges on a particle that's indistinguishable from trillions upon trillions of others, yet is forced by the deep rules of quantum mechanics to carve out its own unique existence. What does that tell you about how reality is put together? It's quite something to ponder.